Welcome. Have you ever looked at that long S symbol in calculus, the integral, and just felt intimidated? Yeah, you are definitely not alone. But what if I told you that by the end of this, you'll be solving them step by step? Today, we're going to break down integral calculus and turn that confusion into confidence, one simple rule at a time. Let's get right into it. So, what does it actually mean to integrate? Well, think about it this way. If differentiation is like finding the car's speed at a specific moment, integration is the reverse. It's like knowing the speed at every single moment and using that to figure out the total distance the car traveled. We're finding the antiderivative, which is just a fancy way of saying we're finding the original function. This is the secret to calculating the exact area under a curve. Here's our game plan. We're going to build your integration skills from the ground up. We'll start with the absolute easiest thing, integrating a constant. Then, we'll unlock the power rule. That's the real workhorse you'll use all the time. After that, we'll see how to handle longer equations, combine all our skills, and finally, tackle definite integrals to get a single concrete number. Every step builds on the last, so by the end, you'll see how it all fits together perfectly. All right, let's lay down the foundation with our very first building block, integrating a constant. This is as basic as it gets in integration, and the good news is it's super intuitive. The rule for integrating a constant, any plain old number, is about as easy as it gets. You just stick an x next to it. But wait, look at that formula. What's that extra plus c doing on the end? That little guy is called the constant of integration, and trust me, it is super important. Let's find out why. So why do we need that mysterious plus c? Okay, let's think backwards for a second. What's the derivative of 7x? It's 7. Simple. But what's the derivative of 7x plus 10? It's also 7. And the derivative of 7x minus 100? Still 7. You see, when you find a derivative, any constant number just vanishes. So when we go in reverse, when we integrate, we have to add that plus c as a placeholder for whatever number might have been there. It represents a whole family of functions that all share the same derivative. In practice, this is incredibly straightforward. The integral of 7? Easy, 7x plus c. The integral of negative 12, you guessed it, negative 12x plus c. You just take the number, attach an x, and slap on a plus c at the end. That's all there is to it. All right, we've got constants down. Now it's time to level up and deal with variables that have exponents. This is where we bring in the real powerhouse of basic integration, the power rule. You're going to be using this one constantly. The power rule is basically a simple two-step recipe. Step 1, add 1 to the power. Step 2, divide by that new power. That's it. That's the whole rule. Let's see it in action. Let's take the integral of x to the 7th power. Step 1, we add 1 to the exponent, so 7 becomes 8. Step 2, we divide by that new exponent, 8. And what do we get? X to the 8th all over 8. And of course, we can't forget our good friend plus c. Now you might be wondering, does this work for negative exponents? Absolutely. The process is exactly the same. For x to the negative 3, we add 1 to the exponent. Just be careful with your signs here. Negative 3 plus 1 is negative 2. Then we divide by that new exponent, negative 2. After a little bit of tidying up, we've got our final answer. And this is where the power rule gets really cool. It works for roots and fractions too. There's just one crucial first step you always have to remember. Before you do anything else, you must rewrite the problem so that everything looks like x raised to a power. Okay, look at this one. The integral of 1 over the square root of x. At first glance, this doesn't look like a power rule problem at all, does it? But we can make it one. The square root of x is the same as x to the power of 1/2. And since it's in the denominator, we can write it as x to the negative 1/2. And boom, now it's a power rule problem. We add 1 to the exponent, divide by the new exponent, simplify it down, and we've cracked it. Okay, we've totally mastered integrating single terms, but what happens when you have a long expression with a bunch of terms being added and subtracted? This is where we learn to combine our skills. This rule is awesome because it's all about making our lives easier. If you have to integrate a long chain of terms, you can just break it apart, integrate each little piece by itself. This lets us turn a big, intimidating problem into a bunch of small, easy ones that we already know how to solve. Let's look at this example. We have 3 terms, so we're going to handle them one by one. First, the power rule on 4x to the 5th, then the power rule again on negative 3x squared, and finally our simple constant rule on the 8, We just combine all those results, clean it up a bit, and add a single plus c at the very end to cover the whole thing.
All right, this is where it all comes together. Think of this section like a practice test. We're about to use all three rules we've learned, the constant rule, the power rule, and the sum rule, to solve a complete problem from start to finish.
Here's our problem. First, we use our sum rule to split it into 3 easier integrals. Now we just go down the line term by term. The integral of 5x to the 4th becomes x to the 5th. The integral of negative 6x to the negative 2 becomes positive 6x to the negative 1. And the integral of 9 is just 9x. Put it all together, rewrite that negative exponent to make it look nice, and add your c. Perfect. All right, time for our final concept. Everything we've done so far has given us an answer that's a general function, right? Something like x squared plus c. But what if you need one specific concrete number as your answer? Well, that's where definite integrals come into play. The first thing you'll notice are the little numbers at the top and bottom of the integral sign. Those are called the bounds of integration. They tell us the exact interval we care about. And because we're finding a precise numerical value, we no longer need the plus c. It would end up canceling itself out anyway, so we can just leave it off. So let's take on our final boss problem, the integral of this function from 1 to 2. And here's the great news. The very first step is exactly what we've been practicing this whole time. We're just going to integrate the function on the inside, and for a moment, we'll completely ignore those bounds. Okay, let's use our rules. 3x squared integrates to x cubed, negative 4x integrates to negative 2x squared, and 5 integrates to 5x. We usually put the result in brackets, which is just our way of saying, okay, the integration part is done, it's ready for the next step.
Now it's time to bring back those bounds we ignored. The process is simple. We take our integrated function, and first, we plug in the upper bound, in this case, 2, everywhere there's an x. Then, we do the exact same thing for the lower bound, which is 1.
So let's run the numbers. When we plug in x equals 2, the whole expression works out to 10. And when we plug in x equals 1, we get a result of 4. We now have our 2 key values. And the final step is the easiest part. You subtract the lower bounds result from the upper bounds result. So we take 10, we subtract 4, and we get our final answer, 6. That's it. We found the exact numerical value of that integral. And just like that, we're done. We started with the simplest idea, a constant, and built our way up, piece by piece, to solve a definite integral. You now have the fundamental toolkit for integral calculus. You've mastered the building blocks. The only question left is, what are you going to solve next?